All right, next up on the docket is talking about variability. So variability is separate from central tendency, but it kind of goes together. Variability is the idea that scores in a data set, like the one that we just looked at, 2, 4, 6, 8, 10, that they're not all the same score, even though not the same score as the median or the mean. In the number of dreams that students had, the mean, median, and mode were different. And so what we know is that scores are variable. Variability also needs to be able to be quantified. So we need to be able to say this data set has numbers that are far different from each other, and this data set has numbers that are all really close together. Those are some ways of describing variability. Just in general, variability is the most interesting part of data. Why we collect data isn't to know all the same thing, but it's to know the edges, the nuances, the differences. And those are what make life interesting, is that there is difference, there is variability. Anybody that tells you we're all the same is lying to you. Just like anyone who tells you that life is anything other than pain is trying to sell you something.
You mock my pain.
Life is pain, Highness. Anyone who says differently is selling something.
Anyone who tells you we're all equal hasn't really been looking around. Equal on what? Thankfully, our government is set up on a principle not that we always follow, not that we always meet, but that all men are created equal with respect to the rights granted to them by their Creator. That they have the rights to light, liberty, and the pursuit of happiness, which if you read Locke just means you could own property. So all sorts of things to debate about that. But what's not able to be debated about is that what makes life interesting is differences. And that's what variability is talking about, is how are things different? How do they vary? How are they not the same? That's what's interesting. That's what we want to learn about. And that's what we're going to cover here with variability. The first measure of variability we're going to cover is something called range. So range, the book is going to tell you something a little bit different than I'm going to tell you. The book is going to say take the highest number in a data set and subtract from that number the lowest number. Okay, I mean, I guess you could do that. There's a problem with that. So imagine, if you will, I have two data sets. One data set looks like this. 2, 4, 6, 8, 10. Okay, so that's one data set. If we took the highest number and we subtracted the lowest number from it, that would give us our data set has a range of 8. I guess that's helpful. Let me show you the problem here. What if I had not this data set, a different data set? A different data set. This data set's totally different. $100,000,002, 100,000,004, 100,000,006, I'm going to keep doing it. 100,000,000, that's a 6, 8, and 100,000,000, 10. So if we do what the book tells us to do to find a range, and we just take the biggest number, 100,000,000, 10, and we subtract from it the lowest number, 100,000,000, 2, we're going to get the same range. Now, I don't know if you're okay with that, because these are vastly different data sets. And the reason we would want to know variability is because we want to know the nuances of things. We want to know how different are these numbers from one another. These numbers 2 to 10, different as 8, that's quite a difference across 2 to 10 given their range. Whereas 100,000,002 and 100,000,010 are really close together given the size, given the scope of those numbers. The range here really shows us that it's not a great measure of variability because it's susceptible to how big the data set is or how large the numbers are in the data set. It gives a relative understanding of variability in that data set, but it doesn't do one that's sufficient to really understand nuances around how do these numbers vary away from one another. And that's really what we want to determine. Now, one way to solve this is a simple one, right? So a simple way to solve the range is instead of just reporting the range, highest number minus lowest number, 8, you could say, write out the highest number, 10, 2, and 8. That way, everyone would know the highest number, the lowest number, and the range. That's a really good solution to this because 3 numbers gives the real insight here to how far do these numbers differ from one another. Or if you, it would be harder here, but you'd write 10, 100 million, 10, 100 million, 2, 8. At least then we would have the information of how far these numbers vary in relationship to each other, and we would have the range. I'm not a big fan of the range. I'm gonna have you calculate it once. I think you all get it, but there's something else you should get that's much deeper than this stuff. Okay. The next one we're going to talk about is something called variance. So what we need to be able to do, or actually what we find ourselves needing to do, is to quantify how is this data set variable compared to other data sets. Like, how much do these numbers differ from each other, and is that distinctive from, say, other data sets of this same variable? What we're going to do is look at variance, which is one way to describe that problem. Variance gives us a number that quantifies, okay, how far away are these numbers from one another? For example, we have the data set, remember that one, 1, 3, 3, 7, or I'm sorry, 6, 7, 7, 8, 8, 8, 9? And you also have that other data set we use, 2, 4, 6, 8, 10. Well, how far apart, how much difference is the variance in these two? We need a number that can say this one or this one has more variability in the numbers. And that's what variance is. Variance gives us a number that quantifies how much difference there is amongst the numbers of a group. Let's do the simple way. We've got 2, 4, 6, 8, 10. We know this is x, right? So x is here. You guys can't see that because, well, I've zoomed in too much. How's that? Cool. Let's see about this. That's a little better. Seriously, who left their phone on in class? I see you. Don't touch that phone. This is mine. Hello, random potential spam from Florida. I'm trying to teach a class here. They didn't answer. All right, put away your phones. Mine's gonna be on. I might cut this part out, I might not. Enjoy. 2, 4, 6, 8, 10. What we need to know is how much variability is there? How do we quantify a number that says how far are these numbers disparate from one another? We know that the average is 6, right? Because we already did that before. We added it up. It was 30. We divided by 5. Remember we did that? We added it up. 30 divided by 5. So that's 6. Now, we can take that 6 as sort of a marker of, well, we can use it as that reference point to say how far away are all of these. So if we take the mean and we subtract from each of these scores the mean, we're going to get what's called a deviation score. So DS, sorry, that's a bad S. DS is deviation score. Deviation score means how far does the raw score, X, deviate from the mean of the group. So 2 obviously deviates -4. So we can write here -4. If you remember, we already kind of did this. I'm trying to build upon this idea so that you guys see how the things kind of are constructed. 4 is different from 6, again, -2. 6 is not at all different, so we don't need to do it, right? Well, no, because 6 is actually a part of this data, even though the number 6 is the mean of that group. So 6 minus 6 is 0. The deviation score of 0 is an important one because it tells us that this number in the data set doesn't differ at all from the group. So that's going to reduce the variability of these numbers. 8 minus 6, that's +2. And 10 minus 6 is, well, +4. We said that a principal function of the mean is to make itself equidistant from all the numbers at one time, thereby ensuring that deviation scores add up to 0. The sum of deviation scores will always equal 0. -4 plus -2 is -6. -6 plus 0 is -6. -6 plus 2 is -4. And -4 plus 4 is 0. If you've gotten this number, you've done it correctly. So congratulate yourself. Good job. You're a math genius. Maybe. This is something that acts as a check for us. If our deviation scores do not equal 0, remember, this is just an example data set. I'm just doing this to show you the process of it. Real data is much more complex than this and will not be as so pretty and easy and, even, so to speak. These are all even numbers. That was a math joke. You're trying to liven it. Come on now. Give me a little bit of love. I'm trying to make this interesting. The sum of deviation scores will always equal 0, and this is a great check to know that we are doing the correct math. However, the sum of deviation scores for all data sets will always be 0. And that's not a number that represents how much these numbers differ from one another. We know that they differ from each other. But what we need to do is kind of find the average amount that they differ from each other. So what we're going to do is we're going to take these numbers, the deviation scores, and we want to get rid of these negatives. The reason we get rid of these negatives is then it will give us a relative distance. Now we will have transformed the number. That's fine. But it gives us a relative number to express how far away 2 is from 6. So if we square these numbers, we get what are called deviation scores squared. So -4 times -4 equals 16. That's nice because when we add it up, it's not going to be 0 and say that there's no variability. It's going to give us an actual number that aggregates together that we can compare to other groups of similar data and say, does this group differ more or less than that other data set? So we take the mean, we subtract from each individual data score the mean of the group. That gives us deviation score. We square deviation scores. And so -2 times -2 is 4. 0 times 0 is 0. 2 times 2 is 4. 4 times 4 is 16. So when we add this up, we get 40. How did I do that? I did it super quick, tricky. 16 plus 4 is 20. And then there's another 16 and 4 here. So it's just 20 plus 20. It's this trick math stuff for you here. Super smart professor. Okay, 40 is the sum of squared deviations from the mean. A way to abbreviate that is SS. The sum of squared deviations from the mean. We're looking at the distance away each individual score is from the mean. We've squared it so that it gets rid of the sort of valence of more or less, and it really says how far. And then we're going to add it up so that we have an aggregate number here that tells us, if we compared this to other groups of 5, we could see if these numbers differ more, i.e. they have a larger sum of squares than other groups. There's one last step, and that is that we have to say sum of squares. What if there were 20 numbers here and the sum of squares was 40? Well, there's only 5 here. That means that the group of 20 who had a sum of squares of 40 would have far less variability in it than our group does. They would almost all be the same number. So many of them, but we have so few. We have to compare this to like size groups. So to get variance, variance is abbreviated SD squared. That makes no sense right now. Be patient, it will make sense. SD squared is the sum of squares divided by n. That's it. Sum of squares divided by n. The sum of squares divided by n. You're comfortable with n, you're comfortable with sum of squares, we did it right here. There's another way of writing this. I'll do it over here so you won't freak out. If we write out what we're doing here, we could say that the variance is equal to sigma x minus mean quantity squared divided by n. That is the formula for variance, but it looks weird. So, you know how to do it. You take this number, 40, and you divide it by how many scores there are. 5. 40 divided by 5 equals 8. The variance for this group of scores is 8. That looks weird. That was easy to do. So if this gets in your way, you don't really need it. It's only helpful for us when we think about what it is that we're doing or how to follow the steps to get it. We take the raw score, x, we subtract from that score the mean, we then take the deviation score and square it, and then we sigma add it all up. After that, order of operations, we divide. That gives us variance, SD squared. Okay. You've done the hard stuff. You've weathered the storm. So now we're going to get to the one that everybody wants to know about and probably has heard of before, which is called the standard deviation. So standard deviation is an important statistic that often in conjunction with the mean is used in inferential statistics. Because of its principles, what it does is also rad. Just like the mean, how it makes itself at one time equidistant from all the numbers in the group. The standard deviation, okay, I'm going to say it, you can just, I guess you just hit the back and the DVR button or the, I don't know, there's a little minus 30 seconds or something on your screen. I don't know where you're watching this. The standard deviation is the average amount that an individual score differs from the mean of its group. Okay. I'll say it again, that way you don't have to rewind. The standard deviation is the average amount that an individual score differs from the mean of its group. So again, let's start with our favorite data set. 2, 4, 6, 8, 10. We know that 6 is the average. So how much does the individual score differ from the mean of its group? Okay. How far is 2 away? We know that, -4. How far is 4 away? Well, we know that, that's -2. How far is 8 away? Well, that's +2. And how far is 10 away? Well, that's +4. Okay, so we just add those up and, oh, you remember, if we add up deviation scores, we get 0 because these that are lower than the mean would have a negative valence, and then it just adds up to 0 for every data set with the mean. So we squared them to get rid of those negatives. So now if we want to get back to an individual level, or a number that represents how far each of these are from the mean of its group, including 6 not being at all away from 6, the mean of the group, we have to take the average amount an individual score differs from the mean of its group. So all we do is to get standard deviation, that's the abbreviation for standard deviation is SD. Come on in close. Get in here. Get in here. Let's do this. To calculate standard deviation, we take SD squared and we take its square root. Bam! That's it. That's all you do. So you just remember how we squared it initially? Now we're going to unsquare it. You take its square root. We squared it to get rid of these negatives because, well, those negatives didn't give us a number that said how far as an individual score does that number differ from the mean of its group. If we just take the number that quantified the variability in the group and then we unsquare it, it gives us the average for each individual score and how they differ from the mean of the group. You might need to watch this part a couple times because it's true, but it's tough to follow the words that make sense. Calculation's easy. The formula's easy. Once we've done that variance one, which isn't difficult, we're going to do that for the rest of the class. That same sort of take the mean, we'll subtract the mean from each individual score, we'll get the deviation score, we'll square the deviation score, we'll add that up for sum of scores. We're going to do that for the rest of the class. So maybe not by hand. Now you have to do it by hand. Later I'll show you there's computers tricks that do it. But this is easy. Take a square root of that variance and that gives us standard deviation. So we know 8 was the variance. So if we take the square root of 8, it's going to give us the average of this. Okay, Google, what is the square root of 8?
Square root of 8 is approximately 2.828.
Thank you. 2.8. They said 2.8, but I don't know. I'm going to leave it like that. Maybe we should go like this. There we go. That's better. Rounding. Okay. This isn't chemistry class. We're not working with significant figures, figuring out molecular weights. And oftentimes mathematicians are too stingy on their specificity for numbers. Depending on the context, you should be careful about how specific you are with numbers, but here's a general rule. Only round at the last answer. So if the question was, what's the standard deviation of these numbers? Only round here, right? 2.82. It keeps going. 2.8282828 for forever. It extends literally forever. So you could do that if you want. This just means that keeps going that direction forever. Forever's too big for you to remember, so maybe you just round it. 2.83. If you put either of those things on a test, I would give it to you. So don't stress about rounding. If you wanted to write out 2.8, 2.8, 2.8, 2.8, 2.8, you're going to be wasting your time on a test. So square. 2 decimals, that's all I need for almost everything in the class. Just remember, 2 decimal places. Here's what I don't need. If the answer was 2, let's say the answer was 2, I absolutely do not need you to write 2.00. That's nothing. You've just wasted ink. You've killed squids for nothing. Well, I don't know what dry erase. I don't know, it's probably not ink because it doesn't smear well, it does smear, but it goes away. All right. If it was 2, just say 2. You don't need to 0.00. But it's 2.8. Let's just round it up and say 3. That's as specific as you need to be. I'm much more concerned with you understanding that this number represents the average amount that an individual score differs from the mean of its group for this data set. That gives us something to work with. That gives us something that we can actually do mathematics with. The specificity of the decimal places is irrelevant right now. We can refine ourselves and get better later. And computers enable this to happen at a much, much more specific level than I'm willing to calculate out by hand with you on a whiteboard in my parents' basement.